Today is the second day of the PyData conference, and we are joined here today by Adam. He is a quantitative developer in Point 72, and we'll be talking more about CSP, so let's get started.
Thank you. Okay, thank you all for coming to my talk this morning on straightforward stream processing with CSP. So in this talk, we're going to look at why it's often more difficult to work with streaming data or real-time data in comparison to static data, and how CSP, which is a new open source Python library, seeks to address some of these challenges. So we'll first look at some basics of stream processing and contrast this with static data analysis, which I think most people are more familiar with. We'll then see how this poses some challenge in the development process when you're building real-time data pipelines. So these are development challenges, like debugging your application, writing unit tests that you can run in a CI pipeline, maybe tuning the performance if you notice that there's bottlenecks in your pipeline, and also making pipelines that can be interactively executed using tools like Jupyter Notebooks. We'll then look at composable stream processing, or CSP, which is a new Python library that seeks to remove some of these obstacles by taking a slightly different approach to stream processing. So the main goal of this talk is really to add a new tool to everybody's data science toolbox. As a data science practitioner or a software engineer, we all have a toolbox of libraries and frameworks that we know really well. And whenever we have a technical problem, you kind of reach into that toolbox, you select the right tool for the job, and you apply it. The issue is, I'm sure some of us are familiar with the saying, if the only tool you have is a hammer, then everything will look like a nail. So if the only tool that you know is pandas, then all data probably looks like a data frame. And oftentimes when you have dynamic data, this isn't the best way to formulate a problem, and it's also not the most effective way to build a real-time data pipeline. So in part of this talk, we look at situations where stream processing techniques make more sense for building your own applications. So a bit about myself. I'm currently a quantitative developer at Point 72, which is a hedge fund here in New York. We work very closely with Cubist Systematic Strategies as well, which is the quantitative investing wing of our company. And together with Cubist, we developed the CSP, or Composable Stream Processing Library, in the firm. So I've been a contributor to this project since I joined the company back in 2022. And initially, I used CSP predominantly for streaming data in the form of market data, so live price updates that happen intraday. But I've also now used CSP for some personal projects as well. For example, transit data. The MTA has a very good streaming feed of their train update times, and you can do some pretty cool projects using that data as well. So composable stream processing is kind of a big milestone for us because it's the first open source project that we've made at Point 72, as we're making more projects now as well. It was the result of many internal contributors, many of whom were working on the project far before I joined the company, and also now some external contributors who have been adding more features to our GitHub, which is now public. So the primary goal when we started this project was to improve the developer experience when building real-time data pipelines. Real-time data applications could be anything from production apps that do fraud detection on millions of customers' data to hobby projects like this earthquake tracker, which is showing a real-time display of earthquakes that occur across the world. So what is developer experience? I would personally define it as how easy it is to build a robust application using some tool or some library. This is an inherently subjective definition because there's 2 points of subjectivity. The first is, what is easy? Easiness for somebody may not be easy for somebody else because we all have our own unique experiences and our own personal preferences when we're writing code. And secondly, robustness depends kind of on the situation. So if you are building a big production application, the robustness standard of that is much higher than if you're building a hobby project like that earthquake tracker. So even though it is subjective and a little context dependent, in almost all situations, there are some common criteria that almost all of us would agree on. These are things like, how much code do you have to write to achieve your goal? Less code is almost always better because it's easier to maintain, it's easier for others to understand. Secondly, how certain can you be in your app's behavior? Can you write good tests that are comprehensive that will verify that when you make a change to your application, it's not going to break the behavior that already existed? And lastly, how easy is it to integrate the tool that you're using with other tools that you want to use in your ecosystem? So if a library pushes you into a very narrow path where you have to use a certain set of tools to do what you want, it's overall less usable than a tool which is open-ended and allows you to choose any data analysis or Python library to achieve your goal. So most people here are probably more familiar with static data. Static and dynamic data are two different forms of data itself. And the distinction is that static data are data sets that are known upfront before you run your application. So these are things like census data and a lot of machine learning data sets. For example, one of my personal favorites, the Blueberry Muffin versus Chihuahua data set, which is a computer vision data set, is an example of static data. Even if you do withhold training and testing groups, it's still static because it's known before you run the application. Dynamic data, in comparison, refers to data that updates during the runtime of the application. So these are things like financial markets, where the prices of assets will change intraday and your application has to respond to those changes. It also includes transit networks, where you have delays or schedule updates that will occur dynamically, and something will have to process that to tell you when your train's going to arrive. Now, batch and stream processing, in comparison, are two different methods of actually processing the data. So batch processing refers to periodically processing the data in aggregate. An example of batch processing would be, let's say you're an accountant, and you have a series of transactions. At the end of every month, you journal up those transactions, you record the net inflow and outflow of capital, and then you record your company's revenue for that month. This is batch processing because you're taking individual data points that occurred at some point in time, and periodically you're processing the data in aggregate. So batch processing has the advantages of often being simpler to implement, and oftentimes it can enable some big data optimizations, like parallelization and distributed computing. Stream processing, on the other hand, is an approach where you process your data immediately as it's generated. So this is a big benefit for dynamic data sets where you want to provide immediate results whenever the data updates. And an example of a stream processing application could be those signs that you see when you're waiting for a subway train. Whenever there's a delay on a subway line, they have to send that information to some source which is going to process the data in a streaming fashion so that it can give you real-time updates on when the trains are arriving. So at an abstract level, stream processing looks something like this. You have a series of data sources, which are the input data to your application. You have a black box, which we're going to discuss in more detail, which is the stream processing engine, and you have a series of outputs. The inputs are, in general, asynchronous. And what this means is they have events that occur out of order with each other. In this example here, for example, the red data source has events at timestamp 1 and timestamp 3, but the green data source has events at timestamp 2 and timestamp 3. Ultimately, it's up to the engine to order those events and synchronize them in a way that's reasonable so that you can apply transformations to the data using functions. Also, you probably have some internal state in this engine, variables that you've saved from past data. So you update the internal state as well using the new data, ultimately generating some outputs. Those outputs in real-time applications are usually predictive things like live inference pipelines, or they're descriptive analytics, like you're monitoring something. So this is a very abstract model of what stream processing is, but it's interesting to note that humans naturally process data in a streaming fashion. So whenever we encounter a data source, we process the data immediately as we receive it. Even right now in this room, you can look at yourself as a stream processor. There are data sources that are asynchronous, such as the audio from my presentation, the visuals from the slides, but your brain is able to just synchronize and order things in a reasonable fashion so that everything aligns. It can transform that raw data that's coming in, and it can update the internal state of things that you've already learned about Python or already learned about data analysis. And then ultimately, what you want to get are some outputs, right? You want to have some applications of this for your own work, maybe questions you have for the Q&A session, or insights you have into stream processing in general. So I mentioned the data toolbox, which is kind of the set of tools that we're familiar with and we can apply to data problems. I can kind of break a lot of libraries into 4 categories based on the static and dynamic data distinction, as well as batch and stream processing. So in terms of static data tools for batch processing, there's a lot of well-known and well-developed libraries out there. These are tools like Pandas, Polars, and NumPy, and they all have very developed ecosystems with mature APIs that are intuitive for Python developers. However, you may run into a situation where you have either static data that's too large to store in memory, and you want to do distributed computing on that data, or you have dynamic data that you want to process in batch because you have lots of data and streaming might not be efficient enough. So to do this, you would turn to a library like Apache Spark, Dask, or Apache Hadoop. These are distributed batch processing tools, so they can do distributed computing on batches of data. Then, if that's not enough, you might want to have a unified platform. So these are things that do both batch and stream processing. They include things like Apache Flink and Apache Beam. Apache Flink is predominantly a stream processing engine, but they do have a batch API. That's why I put them in the category. They're kind of on the cusp of the third and fourth categories there. Beam is batch and stream, so hence Beam. So it's really a truly unified platform for both batching and streaming your data. But you might have a real-time deployment where you want to just use a pure stream processing tool, which will optimize the deployment of your application. And these include tools like Bytewax, Quix, Faust, and Kafka. So where does CSP fall into this toolbox? CSP is a stream processing library, so it falls into that fourth and final category. But the distinction is that CSP works equally well for both static and dynamic data. So this is kind of the key defining feature of CSP, is that you can transition between a historical workflow, which you might be using for research or testing, to a real-time workflow, which is the actual deployed application. So why did we make this decision when we designed the library? I mean, streaming data itself is almost inherently dynamic. You're streaming data and you're processing that in a stream process because you want immediate updates based on the dynamic data. So why would you care about static data in a stream processing library? Well, something that we have observed is that at all stages of the development process, before you actually deploy the application, static data is almost always easier to work with. So for example, if I want to whip up a quick and easy prototype of my data pipeline, I'm just going to give some nice and easy serialized data, make sure that what I get out is reasonable, and then iteratively build more and more stages of that pipeline. Then, if I want to do some extensive back testing on my pipeline, maybe I have some predictive model and I want to see how it would have performed in the past, I again turn to static data, because I take very large time series files, replay the data, and then evaluate my performance. Thirdly, if I want to test my app before I deploy it, which is always a good idea, then you want to have a set of test cases that hit certain corner conditions. And to verify your app's behavior, you again use static data. This goes hand in hand with writing continuous integration tests that are stable. So if you have real-time data sources, they're often coming in over some network connection. It can be down, and then you get noisy failures in your tests. And lastly, if you want to do some performance improvements to your app, and you want to benchmark to see if it actually made it faster, you again want to have the exact same data every single time you run the benchmark, and to this, you use static data. So the CSP development cycle looks a little different than how people would normally build research-intensive applications using other stream processing libraries. Kind of historically, if you wanted to do something that's very research-intensive, you would do static data analysis on your historical data using libraries like pandas, polars, or machine learning libraries. You would then get a model or a set of parameters, which you then use in a real-time deployment, where you rewrite the code to fit the real-time model. The issue with this approach that we observed is if you have a research process that's very iterative, so you're constantly going back and forth between your deployment and tuning parameters or updating something, you then have to go back into your static data analysis library and do the analysis again, update your deployment, go back into the library, update the deployment. And if you have a very iterative process, which we often have in financial research, where you're tuning a strategy over and over again, this isn't too effective a workflow. The CSP philosophy is that you should do all your research, your prototyping, and your deployment within one single application. And to actually deploy the application, you just change the parameters that you run the application with, not the logic itself. So why would people take the first approach using a different framework for research? The main reason is that those static data libraries that I mentioned, like pandas and polars, have a very good developer experience. For anyone who's worked with them, they know that the API is very intuitive. It's easy to write a very small amount of code and get a lot done using those frameworks. The streaming data libraries are generally focused on optimizing the deployment of your application. They're not as focused on enhancing the development experience of building out a pipeline. So I'm going to show a couple examples. So Flink is a very common streaming engine, and their Python API is called PyFlink. If I wanted to have some test data in a CSV file, and I wanted to read that data into my application, this is what the PyFlink code looks like. This is not code that I wrote, because that would be unfair. This is code from their tutorial examples. And as you see, it's 10 lines of code. It's not exactly intuitive on how you're doing this. You call this build function twice, and overall, it's a lot more complicated than what you would do in pandas. In pandas, you would just call read CSV. It's intuitive, it's Pythonic, and for a new user, it's a lot less daunting than having to write code that looks like that. Let's say I wanted to debug my application. The first thing I'd probably do is start printing some stuff out or logging values to see what different values are in the application. If I wanted to do this in Python, I would create an output sync to print values, again from their documentation. And as you see, it's 8 lines of code. It's not exactly conducive to quick and easy debugging. Whereas in Pandas, you do the simple Pythonic thing, which is you call print on your data frame. You get all of the data displayed to you, and you can identify any anomalies that could potentially be causing errors. So the CSP solution to this is to make the streaming data library experience more similar to the static data library APIs that we're all more familiar with, instead of focusing mostly on the deployment. So in CSP, if I return to those 2 examples, if you want to read a CSV file, you create a CSV reader, and you just subscribe to the data. You provide it with a type. This is just because CSP is statically typed. The engine itself is in C++ for performance. So other than that one kind of complication of subscribing to a type, it looks much more like Pandas does than something like Flink or Beam. Similarly, if I wanted to debug my application, I have some stream of data and I want to see what the values are, I would use the csp.print function, which again looks a lot more like the Pandas API than it does like the Flink method of doing it. So the next few slides, I'm just going to do a brief walkthrough of CSP so that we get a feel for how the code kind of looks and how you build an application. CSP at its core is a computation graph framework. And what this means is you have a directed acyclic graph, or DAG, of functions that will execute in your pipeline. We use terminology in CSP, which is a little unconventional. So a lot of libraries will call inputs sources, or Bytewax will use the term connectors. In CSP, we call them input adapters. And they're simply entities that bring data into your graph from some data format. Nodes are functions, generally Python functions, that just transform the data once it's already in the graph. And output adapters are entities that take data from the graph and send it to some other data format. For example, print is an output adapter because it's writing the data to standard out. You put these 3 entities together, and what you have is a csp.graph. And this is the actual CSP application. So a very simple hello world example in CSP looks something like this. I use the csp.graph decorator to declare that this is a graph. I then get an input stream. So I'm going to use the constant here, and I'm going to have the string hello world. The lettering is all messed up though, so I'm going to apply a node to put this into title case. And I use the csp.apply built-in function to do this. Again, I provide the type as string because it's statically typed. And then I use an output adapter, which is csp.print, to actually print that message to standard out. You can visualize this pipeline using showgraph in CSP, and what you get is what you expect. A very simple pipeline with an input, a node, and an output. So if I run this pipeline in real-time mode, I use the csp.run function. I provide my graph. I set the start time to now, and this real-time parameter to true. What this is going to do is it's going to run the application in real time. So I get the message hello world at the time that I actually run that application, since it's a constant value, so you get it at the beginning. Let's say you wanted to run this on historical data. You can actually run this application on historical data without changing the application itself. So generally in CSP, when you're transitioning between historical and real-time execution, the only thing you need to change is the input data source. Here, you actually don't need to change anything because we're using a constant anyways. And CSP is able to achieve this feature by keeping a concept known as engine time. So engine time is essentially self-awareness in the CSP application of whether the application is running in real-time mode or if it's running in historical. This essentially allows CSP to transition between simulated data, where you're replaying data with a certain timestamp, and real-time data, where it's getting in from a real-time data feed. So you can transition between these 2 modes by setting the real-time parameter here to false. And you can run this pipeline on some date, like 2022 in the past. And what you'll get is the same hello world message, but you'll get it back in 2022. You can imagine doing this approach with a couple of years worth of recorded data, and this will allow for testing, generally during the research process of your application. So CSP nodes are just Python functions that transform.
Is there something else I can help with?
I don't know why Siri is updated there.
Here's some news.
Okay, we're back. Sorry about that. So Nodes themselves are functions, just like any other Python function, that transforms time series data. Time series data is essentially a basic data type in CSP. You have typed time series, which are typed streams of values. And to create a CSP node, all you do is essentially create a Python function. There's 2 extra steps you need to do here. So the first is you add the csp.node decorator to signify that this is a node. And then you just have to type your input values. So a lot of people will do static typing in Python already because it's good practice, but in CSP it's mandatory. Once you've done these 2 things, it's just a Python function. So you can use any Python library, you can write standard Python code. This node is converting strings to Pig Latin, so this is just standard Python. And when you return your Pig Latin string, it's going to emit another time series of strings, and this is going to propagate to any downstream consumers in your graph. So I can create a graph called Hello Hey Old Way, which is going to be building on that Hello World application. It's going to take in 2 constants, which are hello and world, convert each word individually to Pig Latin using my Pig Latin node or function. Then I use this built-in flatten function from CSP, which collects multiple time series and unrolls them into a single stream. And what I will get if I run this in either historical or real-time mode is the message Hello Hey Old Way. So nodes are building blocks of CSP applications. You can put together nodes to build graphs, and you can put together those graphs to build even bigger graphs. And oftentimes, in very research-intensive applications, you could have thousands to even 100,000 nodes in your application. It's quite hard to reason with unless you take a somewhat modular structure of development. So the idea of composable stream processing is that you compose your nodes into subgraphs. You compose those subgraphs into bigger graphs, and then ultimately use that to build out your application. You often have structures where you have multiple data sources and you apply the same subgraph to the data, so you can reuse subgraphs. And this is kind of just a more Pythonic way of building an application. Often when you're writing Python code, you don't want to have one big function, which is doing all of your analysis. You want to build it off with smaller components that are easier to reason with. So as I mentioned, the CSP engine is written in C++ for performance reasons. We also include a series of nodes that are pre-written in C++. So these include common operations like control flow operations. This would be things like filtering a data stream, sampling a data stream, merging 2 data streams together, things like that. We also have real-time statistics calculations. So these are rolling window aggregations, like rolling averages and things like that, which are, again, very common in stream processing applications. And we also provide some of the input and output adapters for you to use out of the box. So these are mainly for common data formats, things like Parquet, which is a very useful source for historical data, things like Kafka for real-time, which is a very common message format, and Perspective, which is a real-time visualization output adapter where you can visualize things in real time. For example, the earthquake example that we'll look at is using Perspective to achieve that. So a couple limitations of CSP, in my opinion, compared to tools like ByteWax or Flink. The first one is that we have fewer pre-built adapters for different data formats. So libraries like ByteWax have very broad support for things like cloud storage formats like S3, various database formats, and things like that. The goal of CSP is that you can write the adapters yourself. So we have lots of examples on how you can build adapters in either Python or C++. So we provide fewer data formats out of the box. So if you are looking for out of the box S3 adapter, it's not going to be included in CSP. The other thing is our developer API. So it's only exposed in Python at the moment. This is a PyData conference, so hopefully that's not too much of a limitation. But if you do like Java or Go, Flink and Beam have APIs that support both of those languages, and we don't. And the third thing, it's not too much of a limitation, but more of a design choice. So when you have CSP applications, you can execute the graphs themselves in parallel, but you can't execute nodes within the graph in parallel. So this is kind of something we learned by attempting to do it, is you kind of have 2 types of nodes, right? You have Python nodes that users have written, and those require the GIL, so you can't really parallelize them. And then you have C++ nodes that we've written, and those are usually really fast, so it's not worth running them on a separate thread. So it's kind of more effective to have multiple disjoint graphs that run in parallel pipelines if you want to have distributed or parallel compute. So this brings us to the more interesting part of the talk. These are kind of the 5 areas where I think the CSP approach enhances the developer experience when you're building a real-time data pipeline. So these areas are research before your deployment, debugging the pipeline when inevitably something goes wrong, writing unit tests for that pipeline, so hopefully you don't need to debug it, optimizing your performance if you notice that there's bottlenecks in your pipeline, and also running a stream processor in interactive Python. So using tools like Jupyter and Jupyter Lab to have notebooks that run these pipelines. So the first topic is research before deployment. And I've kind of alluded to the whole concept of backtesting, where you often have some predictive model that you're running in real time, and you want to evaluate how this model would have performed if you used it on past data. So to do this, you take very large time series files, and you replay the data through your application. And because of the way CSP supports static data, it makes it very easy to do. All you have to do is swap out your input adapter to some Parquet or CSV file, and you can replay the data very naturally. CSP will handle all the ordering of the events and synchronization in historical mode so that you don't have to do it. And all you have to really write is the application logic of the transformations you make to the data, which are in nodes. So an example where this was helpful was I was looking at the subway data, and I was wondering if I take the average across all subway stations in New York City, what's the average time that you have to wait for a train at different points in the day? So the subway feed has 8 different endpoints, which are all out of sync with each other. So even though this was historical data, it's useful to use CSP because it synchronizes and orders the events. And then I can get a nice plot like this, which shows that on average, you're waiting less than 5 minutes. But if you get really unlucky, you're probably waiting 30 minutes. Another advantage of using CSP for research is the removal of look-ahead bias. So in time series analysis, look-ahead bias refers to using future data in your historical prediction. An example of this would be if I want to evaluate how well my transit route planner performs. So I provide inputs to that model, which are things like when the train arrives and stuff like that. That would be an example of look-ahead bias, because I can't use when the train arrives to predict the route. I have to use when the train was scheduled. If there were delays or schedule disruptions, I would not have known of those at the time that I made the prediction. So it's actually biasing my model that I'm using that data in historical evaluation. Because of the way CSP replays the data sequentially, you never have access to future data at any time point. So you essentially remove this possibility that you have bias in the research. Secondly, debugging. So oftentimes you have some stream or some data which can crash or error in your application. The CSP approach, because we have this kind of iterative design philosophy, is if you have that stream, you can replay the data statically, so it's fast, you can write through it, and hopefully it replicates the error. You can use the csp.print and csp.log functions as well to inspect any stream of data. And you can use any debugging tool of your choice. So it makes it a little easier to debug the application if something in the real-time model goes wrong. I'll also note that ByteWax does have a testing source that allows you to do this as well, but the way CSP works with static data, it's a little easier to do in CSP. On that note, unit testing. So real-time data is not optimal for CI pipelines for a few reasons. The first off is it can be very noisy. So if your real-time data feed is down for any reason, then your test will fail, even if your application itself is fine. The second is that it's often not comprehensive enough. You might have some edge conditions that are not going to be present in the real-time data feed, and you have to serialize those yourself to ensure you actually hit all the conditions that your app can see. So static data comes to the rescue here. You can make a Parquet file with whatever data you want, and you know it's going to hit all the conditions you need to test. To do this in CSP, because of the composability feature, you just swap out the data source and the data output. So you have some real-time data source and some complex application that you wrote that has 10,000 nodes. You just take your source, you swap it out for a Parquet source where you decide what the data is. And then you take your output, you swap it out for an in-process output. So this is just returning from the function. And what you're left with is data that you get in Python. You can use PyTest and unit test to verify that the behavior is what you expect. And you can actually test your application without relying on the real-time data. So I'm sure some of us are familiar with this quote: premature optimization is the root of all evil. And often when you're building a data pipeline, you just want to build it and not have to worry about every minute detail of its performance. So CSP takes this to heart, and the idea is that you can build your CSP app as quickly as possible, and if you do have performance issues, then we provide a profiler so that you can inspect your graph and see where the bottleneck is. The profiler takes one line of code to configure, so all you have to do is create a profiler context. You can spin up the profiler on an HTTP port. Then you can run your graph just like you would in historical real time. What this is going to do is create a live profiler on your port. It'll have stats like, for example, which nodes are taking up the most amount of time. If you notice a node's very slow, you might want to write that node differently to enhance its performance. Similarly, it will give you the average cycle time that the graph takes to execute. So if you know that your data updates every 1 second, but your cycle time is 1.5 seconds, you know that you need to optimize the performance or else you're going to fall behind. And lastly, it's not shown here, but you get memory snapshots. So if your app is crashing due to memory issues, it actually shows you where the memory is being allocated from in real time, so you can find those issues before you deploy the app. And the final point in terms of the developer experience is interactive execution. So if you're working with static data, the first thing you probably do is exploratory data analysis. And to do that, you'll often launch a Jupyter Notebook or Jupyter Lab session. You'll take static data and you'll do some basic analysis on the data set. And it's really good to do this in an interactive mode of execution because you can execute cell by cell and see what the data looks like. So CSP is a stream processing library that's fully functional in interactive Python and Jupyter environments. It's useful for both prototyping your app, so exploring the data set and building out a very simple pipeline, but it's also useful for making demonstrations that are interactive. So this earthquake example, which I showed earlier, is actually fully running in a Jupyter Notebook. All of the code there is executed cell by cell, and when you get to that final big reveal of the map, it's again running a widget in the notebook itself. So in summary, stream processing can be hard, but it doesn't always have to be. So CSP tries to abstract away all the complexity of stream processing by focusing more heavily on development than deployment itself. We have over 30 examples on our GitHub if you're interested in taking a look. These include full-fledged applications that we built with CSP, so things like the earthquake tracker and also a couple of examples with Wikimedia data as well. You can install CSP via pip or conda, whichever you prefer. And if you do build something cool with CSP, we've started a group of community projects on GitHub under CSP community. So you can post your project there to share with everyone the cool thing that you've built using CSP. And that's the end of the talk. Thank you all so much.
Does anyone have any questions they want to ask? Or?
What's the volume, what's the max volume that you use? What's the max volume of data that you push through a system using CSP?
I can't give you a number in terms of like bytes per second or something like that, because it really depends on your application. So if you have like a big graph with a lot of logic, of course it's going to be like very different than if you have a very fast data pipeline. But we've been using CSP for a few years with financial market data, so you do have very fast updating data, and you also have data from multiple exchanges. So I would say it can handle a lot of data, but again, it depends on how you build the pipeline. It's very dependent.
Do you guys have any plans, or do you already support some notion of incremental computation where you memorize like pure functional nodes, and then downstream nodes, if they have the same properties, they themselves don't have to do any extra computation?
Yeah, so in terms of I guess there's two aspects to that. The memorization aspect is kind of already present in CSP. And in terms of the incremental execution aspect, I think we have been experimenting with that for more debugging purposes, if you mean incrementally executing nodes and then breaking execution.
I just meant it more in the sense of incremental, meaning that you only modify parts of the graph that need to be modified. So it's basically like memorization but recursive.
Yeah. So I mean, if you have, say, multiple data sources, and only one of those data sources is activated with a data stream, it's only going to schedule its consumers. The whole graph won't execute.
Thank you.
Well, let me start by saying this is really cool. So, thanks for the talk. Maybe taking a higher level question, can you give us some sense of successful applications that built with CSP? And conversely, applications that CSP was just not suited for, or maybe it just doesn't work as well currently and needs some improvements?
Sure, yeah, I can give you some, both like hobby and from my own work. So something that CSP works very well for is like live visualization, because we have the integration of perspective. So if you want to have something which uses real-time visualization, CSP is great for that. It also works well if you have kind of like medium frequency data. I guess I would say that in more financial context. One example where CSP probably doesn't work great is if you have like very high frequency financial data. This is because you probably want to turn to something like C++ to handle that type of data, just because it's a more efficient kind of environment of doing it.
You mentioned the look-ahead bias was avoided. How do you know which columns are looking into the future, or how to do that?
So the way CSP works is if you have multiple data streams, let's say I have parquet file 1, parquet file 2, and the columns don't match in time, the engine itself will only replay the events in sequential order. So the user doesn't have to specify like a time index policy like some other libraries. It'll read the data one at a time from each file and replay it in order, so that even if you have separate columns that aren't aligned time-wise, the data itself will always be sequential.
Thank you. Do you do any graph simplification?
Yeah, so there's a couple optimizations that we do. One of them is pruning. So if you have paths in the graph that don't lead to outputs, those are going to be removed because they're never actually going to be generating anything useful. We also do optimization called memoization. So if you declare the same nodes with the same parameters, they get collapsed into a single node as well to make the pipeline more efficient.
Hey, is it a common workflow for you to develop a graph using CSP, but then have to code it up in some other streaming framework for performance reasons?
We've never had to do that. So the idea is that once you've coded the graph in CSP, you're going to deploy it in CSP as well. And we've never really noticed like a need to go to another streaming application.
Any more questions?
Do you have a sense of like the roadmap for future development of the library, and what the open source community is doing with it?
For sure. A couple things that we're focusing on. One of them, which we recently merged, is making our type system very pydantic. So we integrated pydantic into the library because it is statically typed, and we do type validation. So pydantic was an improvement for this. We also want to have support for more adapter formats that users build. So the idea is you can build an adapter for something like S3 data, host it in your own repository off of the project itself, and then other people can use your adapters rather than storing them all with the project. So making a more easy to use API for building adapters is also part of the project roadmap. Yeah.
I saw Kafka was an output, and can it also be an input, and then can it be a part of consumer group where multiple instances can be running in parallel with the same graph?
Yeah. Yeah.
Well, so he'll be around, right, in the stall on 5th floor? Yeah, so he'll be on the 5th floor if you have any questions later in the day. But I think we are ready to move on, and let's thank him for giving such a wonderful presentation.